This leads us into the idea of mechanisms. And mechanisms is another big part of kinetics because in the rate law we just looked at extensively, we looked at how to find if things were first order, second order, zero order, stuff like that, rate constants. But the question you might be asking yourself is why are some reactants first order and why are some reactants second or zero order, stuff like that? Well, to answer those kind of questions, we really need to look at the mechanism, which is how you go from reactants to the products. Now, the rate law we saw had to be figured out through experiment. Like you've got to go in the lab, try different trials, stuff like that. The mechanism now is really purely theoretical. There's some ways to augment your ideas that you're coming up with theoretically, but really it's about theory. So it's a really cool combination of different things in science. As a useful idea of how this mechanism thing works, on the right-hand side is an example of a skiing area. I think it's a skiing area in Vermont, but I'm not totally sure. People, when they go skiing, they'll go from the bottom base lodge and they'll go up here to the top of the mountain. And from the top of the mountain, depending on your skill level, you can go down different ways. And for reasons which we don't need to go into a lot of detail here, I am a really bad skier. So anyway, if it was me, I would try and take the most gentle loop down because I don't want to go too fast and I'd probably still end up hitting some trees, but I would go down as gently as possible. All right. And then, finally end up way over here in Timbuktu, but eventually I would end up back at the base camp. All right. Now, I'm sure that some of you in this class are like basically world-class Olympians when it comes to snowboarding and skiing, something I've never been. So you'd probably go, straight down. Oh, my pen can't even handle it. It's too intense. But you would go like straight down the mountain. So all of us, you the cool Olympic person and me the pathetic skier, we would both start at the same point and we would both end at the same point. But the path we took to get there was quite different. Yours would have been direct, all right, highest to lowest, as fast as possible. On the other hand, lame me, I was taking, weird things and going through trees and stuff, trying to be gentle because I didn't want to go too fast, all right. Both of us got to the same point, but it was obviously a different amount of time to get there. And chemicals will do the same way. Now, normally we'd probably think chemicals would go the fastest way, but that's not always the case. We can use the rate law to see, are they really going the fastest way or are they going a slower way? And along the way, we can then make sense of what the rate law is trying to tell us, like why some chemicals are first or second. So we're really digging into the way that chemicals go from reactants to products, something we haven't done up to this point. And from that, we'll be able to learn about why the rate law is what it is. Mechanisms can be really important in chemistry. On the right is a graph that shows a reactant on the left and a product on the right, all right? And we have on the left a methyl isocyanide. It's a methyl group, CH3, and it's turning into a methyl cyanide. So this thing right here on the right is methyl cyanide, also known as acetonitrile, and this thing right here on the left is the methyl isocyanide. And methyl cyanide, which is also known as acetonitrile, is a little bit more stable than the methyl isocyanide. Now, the red line right there is the mechanism that scientists have proposed for how methyl isocyanide goes to methyl cyanide. And notice that at first, there's a lot of energy. This is an energy axis, okay? And it takes a lot of energy to get up to some kind of what we're going to call activated complex or transition state. And once you get up there, then you actually get a lot of energy back down as you go back down to the product. Now, if you look at these little pictures, these are essentially kind of Lewis structures, but only the first and the last structure will really make any sense. We've seen in the Lewis structure chapter that if you have a triple bond and a single bond, the electron pair geometry will always be linear, 180 degrees across. And you don't see that on the second picture, which is right here, or the fourth picture right here. You've got more what looks like kind of a 120 degree angle angle. So you're starting to see some really weird things. But if you really want to be freaked out, like in a science fiction kind of way, look at this bad boy. Carbon is connected directly to the triple bond of the CN triple bond cyanide part. And that doesn't make any sense. So a coordination diagram like this is trying to make sense of why isocyanide wants to go to cyanide. And what scientists propose is that the cyanide starts to kind of go up. So the carbon starts to go more 120 and even 90. And that's not going to be a real stable configuration because normally that wants to be 180 degrees apart. So the cyanide essentially shifts down. The triple bond is connected to the carbon bond, which is really, really weird from all the rules we've studied. And then because that's not going to stay that way, the carbon finally ends up connected to the other carbon, but at 120 degrees or something like that. And finally, then it straightens out to 180. Beginning part and ending part will make sense on everything we've seen, but these intermediates in between are going to be all over the place. The highest energy part is called the activated complex, and you're going to see really weird things there. So carbon connected to a triple bond, that's like, whoa, bizarre, man. But it's necessary to understand how reactants go to products. E sub A is going to be important for us. That's the energy of activation, and that's the energy to get up to that activated complex, to get to that super wild part. And finally, the difference between where you start and where you end up, i.e. reactants and products, is going to be a delta E. If that delta E is lower, like it is right now, that means this reaction is exothermic. You're ending up with a lower energy state than you started with. So energy was given off. This is an exothermic reaction. But finally, you can also, at least intellectually, think about going from products to reactants. So methyl cyanide back to methyl isocyanide. You'd have an even bigger E sub A because you'd be starting down here and you'd have to go all the way back there. And at the end, your resting spot, the isocyanide, is higher energy than where you started. That would be endothermic. So these reaction coordinate diagrams, super cool. And we're going to dig through everything I just said in more detail in the next several slides. This picture here shows the difference between the reactants and products energy. And because in the way we're looking at it, reactants on the left, products on the right, which is the most standard, by the way, the final energy is lower than the initial energy. Energy was released. So in this example, the energy of the final was less than the energy in the initial. Energy is released. This is exothermic. But again, if you had it the other way, if reactants were lower in energy than the products, you could have an endothermic reaction. The high point, though, in that diagram shows again what's called the transition state or the activated complex. And at those times, you're going to see the most breaks from all the standard rules we learned in the Lewis structures than we ever had before. That transition state, like kind of chemical looking formula right there, it's called the activated complex. And you're going to see some really wild interactions. You'll see carbon with 5 bonds, which I told you never can happen. In this example, you're looking at carbon bonded to a triple bond, which also doesn't make sense either. So you're going to see really wild combinations. These are super high energy transitions that don't exist by themselves. But if you're going from reactants to products, maybe it's worth it for the molecule to make that cost to get the energy out on the other side. The energy gap, E sub A, between where you start and the highest point in that activated complex is called the activation energy barrier, or the energy of activation. And that's a super important number for chemists. If the K constant was the holy grail of the last section, E sub A is going to be the holy grail of this section. Because knowing about differences in E sub A, you can oftentimes rationalize why reactions are faster and slower. And we'll see that coming up. To understand this energy of activation barrier, I want to use some kind of cheesy real-world examples to show you some of the things that happen. Now remember, all these chemical systems, there's like 10 to the 23rd little molecules bouncing around at one time. So I've got there in the lower part a golfer, all right? And she's trying to get the golf ball over the hill to the hole on the other side. Well, you can imagine that it would be super easy to not hit the ball hard enough. So the ball would like start to go up, but then it would come back down. All right. On the other hand, it's super easy to hit it like too hard. So maybe it would go wider over. The idea is to get just the right amount of energy to get over the hill. And that's where skill comes in and all that kind of stuff. So energy of activation is kind of like that. You want to have just the right amount of energy. And not all reactant molecules will have the right amount of energy. They'll kind of go up a ways, but then they'll go back down. They need enough energy to make it happen. And they might do it a couple times too before it happens. Same thing in the volleyball example. When she's hitting the volleyball there, you have to have just the right amount of energy and the right direction, of course, to get the ball over the net. And if it's not enough energy or the right orientation, it'll just bounce right back. And of course, that's not what you want. So chemicals will do that too. They have to have the right amount of energy, the right amount of direction to get over the energy of activation barrier and become a product. So what that means is not all reactants instantly become products because they don't have the energy and or the direction. Differences in activation energy can be the difference why reactions are fast or slow. If you have a really low energy of activation barrier, then you're more likely to get over the barrier and the reaction will go faster. On the other hand, if you have a big energy of activation barrier, it may take many, many times to get over the barrier, and that's going to make your reaction slower. So one reason why reactions are faster or slower is just the depth or the height, I guess, of the energy of activation barrier. Generally, as temperature increases, so does your reaction rate. Reactions go faster at warm temperatures, and that's really because the value of K, the rate constant, is temperature dependent. So all of the ways we saw earlier to solve K, you could solve them at different temperatures, all right, and you'd have different values of K. So this graph here in the lower left-hand corner, it shows a bunch of rate constants K on the left versus their temperature on the right, and you can see how the value of K is increasing as the temperature gets up. Now, changes in K will help us to find the activation energy barrier, and that's a pretty cool thing.
A solution containing hydrogen peroxide is added to one containing iodide ion and ascorbic acid. This is a clock reaction, where after a small initial fraction of the hydrogen peroxide has reacted, a color change occurs. The same reaction can be performed at low temperature. Under these conditions, the color change occurs after a longer period of time.
This reaction is called the iodine clock reaction. When I2 iodine forms, it makes that kind of dark purple kind of color. And you can see that without ice, it took 54 seconds, but with the ice bath, it took 1 minute and 31 seconds. So generally speaking, reactions do occur slower at the lower temperatures, all right? When you lower the temperature, the individual molecules don't have enough energy to jump over the energy of activation barrier. So it takes them more time to get over it. On the other hand, warmer temperatures, they have more energy. It's easier for them to make the transition, in this case, to the kind of dark iodine color. So if you're going to make bonds, or break bonds for that matter, the reactions have to have, like we talked about, the right energy of activation or activation energy, but they also have to have the right geometry, all right? Like it would have been easy for the golfer earlier to hit it with, the right energy, but if it was in the wrong direction, it might go to another golfing hole or something like that. In a chemistry world, this is also really important. So I want to show 3 videos here, and they're all about the reaction of ozone and nitrogen monoxide to make oxygen and nitrogen dioxide. One of the videos will show when the molecules come together, but with insufficient energy to make anything happen, like you don't have enough energy to break bonds and make bonds. One of them will be the right energy, but the incorrect geometry. And then finally, we'll look at a video where you do have the right energy and the right geometry.
For 2 molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting.
When I give lectures face-to-face, I always come in and I try and have enough energy that I can really jazz my audience, all right, so I can get people excited about chemistry, because don't tell anybody, but sometimes chemistry isn't the most exciting. Anyway, this is kind of, in this particular problem, it's imagine you have like a bunch of tired students and a tired instructor. They're just not enough energy, man. No one's getting jazzed about anything, and it's not going to be the most efficient learning tool. Let's look at an example now that's not about insufficient energy, but insufficient geometry, or the incorrect geometry for this reaction to occur.
If the 2 molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
In this reaction, the nitrogen must collide with an oxygen on ozone to make the NO2. All right, so in this problem, there was enough energy, but it was the oxygen on NO colliding with an oxygen on ozone. And that's not what you need to make the nitrogen dioxide bond. The nitrogen's in the middle of the 2 oxygens. You can draw the Lewis structure. So this is an example where the energy was right, but the geometry was wrong. And you're not going to be able to make a molecule or the products in this case with this incorrect geometry.
If a collision occurs between the 2 molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
So on the right there is an energy diagram or reaction coordinate diagram for what could be this interaction. All right, there's going to be a reactants, I'll just draw it R on the left, and products on the bottom. All right, whoops. There we go. And initially, in the first example, there wasn't enough energy to overcome the E sub A, that energy requirement to make reactants turn into products. And in the second video, the energy was there, but they weren't oriented right. So you can't make the transition state, whatever it is, to make it happen. But in this third example now, ozone and NO were in the right energy, in the right geometry. They were able to overcome the energy of activation barrier, i.e. the NO was able to pull an oxygen from ozone to make NO2, and you ended up making products. Now, this reaction is definitely exothermic, and it's exothermic because the final energy is less than the initial energy, so the E sub A value is like a cost you have to pay to get in, but then you get a lot of energy out. There's nothing wrong with thinking about these reactions in the reverse. So you can see that there's an EA forward, which is what we've been kind of talking about in this problem, but there could also be an EA reverse. Like what if you wanted to make more ozone? You wanted to take oxygen and add NO to it to make ozone and NO. Well, you absolutely could. It would have a very big energy of activation. You'd have to go from the bottom where the now products are sitting, but it would be reactants in our case. It would have to go all the way back up to that transition state. The NO would be essentially giving up an oxygen to make ozone, and NO would be by itself. And then at the end, you'd end up where the reactants are in terms of energy. So that would be an endothermic process with a very large energy of activation. So we would probably predict then that the forward reaction is more likely than the reverse reaction because of the different energies of E sub A. And it's quite a bit different, it looks like. So it's kind of cool to think about how these things work out. it is possible to calculate those energy of activations, forward, reverse reactions, whatever. And we can do that because remember that reactions are generally slower at the lower temperatures. They don't have enough energy to make it over the barriers, and they're generally faster at the warm temperatures. So you can have then these kind of pictures we've seen since the gas laws of showing the different distributions of energies, all right? Let's pretend that this black line right here, kind of in the middle, this is the minimum amount of energy required to make products. So there's more molecules at the warmer red temperature than there are at the colder blue temperature. Some of the blues will have enough energy to become products, but more than there'll be a lot more at the warmer red temperature. And again, differences in activation energy are oftentimes the difference why reactants are slow or fast. But if you have a warmer temperature, you have a bigger fraction of molecules able to overcome that energy of activation and become product. So this guy named Arrhenius studied this in quite a lot of detail, and he came up with what's called the rhenius equation. And it looks kind of funky at first, so let's kind of dig through this here. The rate constants K we've seen and talked about do vary with temperature. And so what Arrhenius came up with is how rate constants K equal a big A, and that's called the frequency factor. And frequency factor is related to the frequency of collisions with the correct geometry. There's more you can do with that, but we're not going to talk about it too much in this class. But anyway, big A frequency factor times E, that's the anti-natural log E, E raised to the power of negative EA over RT. And the cool part for us right now, if you can call it cool anyway, is that, hey, here's E sub A. This is a way to calculate E sub A from values of K. E sub A is a constant. Temperature is changing along with the rate constants K. So A, big A, E sub A, and R are all constants. R here is what I called the energy R in an earlier lecture. It's 8.3145 joules per mole Kelvin, or what's usually done in these problems, 8.3145 times 10 to the minus 3 kilojoules per mole Kelvin. But anyway, this equation is an exponential form, and if you're cool with math, you can use this in all the ways we've seen. But what scientists will usually do is take the natural log version of all that stuff. And you can do this on your own later if you'd like. But when you do that, you can rebrand, if you will, that equation as natural log equals negative EA over R times 1 over T plus natural log of A. And if you're like, Russell, you have totally lost it, this doesn't look any easier than it was before. Well, yes and no, because this new way of writing it here is like a straight line. It's Y equals mx plus b. M is the slope, all right? Negative EA over R equals the slope, which is a cool way to find the energy of activation. And B is related to the frequency factor. B equals the y-intercept equals natural log of A. So if you take a whole bunch of rate constants K and plot them as natural log of K versus 1 over their Kelvin temperatures, you will see a straight line. It'll have a negative slope. Negative slope equals negative EA over R. E sub A is how you find it. And E sub A is always going to be a big positive number. We will do this in lab. It's not hard. It's a little tedious. I won't deny it. But it's totally the best way to find these energies of activation.